Let's look at an example for our series resonance circuit shown below. So for this series RLC circuit, what we want to find are several things. For part A, we want to find our resonant frequency omega naught, our half power frequencies omega 1 and omega 2. Then for part B, we want to find our bandwidth and our quality factor. And for part C, we want to find the amplitude of the current at our three key frequencies we found in part A. So let's get started. So for part A, we want to find these key frequencies. So we'll notice that we have options. So because we presented these alternate forms of equations, we can choose which equations we want to use. What I'm going to do here is I'm going to choose to use equations that have R, L, and C. And so L, C, R. The reason that I'm going to do that is, for instance, let's say I try to calculate using one of the other equations, so maybe I need to calculate my bandwidth first. Well, if I make an error in calculating my bandwidth, and then I use that to calculate my omega 1 and my omega 2, then of course that error is going to be propagated. So again, this is just a personal choice. You're perfectly fine using any of the forms, so long as you're careful with your calculations. So let's start by using equation 1 to find our resonant frequency. So from equation 1, we know that our resonant frequency is equal to 1 divided by the square root of LC. So here we have the square root of our inductor was 1 millihenry, so that's going to be 10 to the minus third. And our capacitor is 0.4 microfarad, so that's 0.4 times 10 to the minus 6. So we plug that in and we get that our resonant frequency is equal to 50,000. And so the units of that are going to be radians per second. And so to make that a little easier to deal with, we can call that 50 kiloradians per second. Okay, so now also for my omega 1 and omega 2, I'm going to be using the forms of the equations that have the R, L, and C. So for omega 1, I have negative R divided by RL, so our resistance value was 2 ohms. So negative 2 divided by 2 times L, so 10 to the minus third, plus the square root. And now we have in our square root, plugging in our values, 2 divided by 2L, so 2 times 10 to the minus third, all of that squared, plus 1 divided by LC, where our L is going to be 10 to the minus third, and our C is 0.4 times 10 to the minus 6. So if we plug that in, we get that our omega 1 is equal to 49,009.999. Again, the units of that are radians per second. Well, that's pretty difficult to deal with and carry around, so let's instead say that that's approximately 49 kiloradians per second. Okay, so now finally for our omega 2, so this is the last thing that we wanted for our part 1. And so again, that form is going to be pretty similar as this, so let me just, instead of not writing it, let me at least just copy this here. And so the only difference is we're going to change the sign out front. So I've got that equal sign too. There we go. So the only difference is we're going to get rid of this negative sign out front, but everything else is going to stay the same. And so if we plug that in to calculate it, we get that this omega 2 value is equal to 51,009.999. That's radians per second. Again, that's very sort of clunky to deal with, so we can just call that 51 kiloradians per second. Okay, so now we have completed part A, and as we expect, we have this omega 1 and omega 2, which are sort of equally spaced out from our omega naught. All right, so moving on to part B, we're now interested in using the bandwidth. So of course, you might say, well, the easiest way to find your bandwidth would be to just subtract omega 1 and omega 2. But for the same reason I mentioned earlier, what I'm going to use is equation 6. And the reason is that goes back to our R and L value. So just in case I made a mistake in omega 1 and omega 2, it's not going to propagate through to my beta, or sorry, my B. So my bandwidth is equal to R over L. So that's going to be 2 divided by, our L was 10 to the minus third. So that's equal to 2,000. And again, units of that are going to be radians per second. To make that a little easier to look at and to match what we had before, let's call that 2 kiloradians per second. Okay, so the other thing we wanted for part B was our quality factor Q. And so again, I'm going to go back to my equation that had all of these terms, all of the Q in terms of our R, L, and C. And so that was equation 5 from a previous video and in the notes. And so that's going to be L divided by square root of L divided by CR squared. So we have 10 to the minus third divided by C, which is 0.4, times 10 to the minus 6, and then times our R value squared. So plugging that in, we get that our Q is equal to 25. And so we note that this quality factor is a dimensionless value. So we don't have any dimensions like volts, amps, radians per second, no dimensions for our Q. Note that previously we said that if Q is greater than or equal to 10, we consider that to be a high Q circuit. So in this case, we would consider this circuit to be high Q, which means that it is very selective. Okay, so moving on to part C then, what we're looking at for part C is we're looking for our current, amplitude of current at omega equals omega naught, omega 1, and omega 2. And so what we're going to have to consider now is this voltage information here, particularly this voltage magnitude of 20. So we know that at our resonant frequency, our current is the max value. So at omega naught, we have our max current magnitude. And so we know that that max current magnitude is equal to just Vm over R. So our magnitude at omega naught is equal to our voltage magnitude divided by R, because at this resonant frequency, the impedances from the inductor and capacitor are canceling out. So plugging in values, our voltage magnitude is 20 volts, our resistor was 2 ohms, so we get that our current at that frequency, resonant frequency, is 10 amps. So now at both our omega 1 and omega 2, we know that by definition, this is going to be our current magnitude equals 1 over root 2 times our maximum current magnitude. And so again, that's just sort of how we defined it in terms of it being a half power bandwidth. So what we can say then is our current at omega 1 equals the current magnitude at omega 2, which is just equal to 1 over root 2 times that current magnitude at omega naught. So that's just going to be 1 over root 2 times our 10 amps. And we get that that is approximately 7.071 amps. And so that's all for that example. One thing to note is that if we wanted to, we could go back to some of those other forms of our equations. Specifically, we could go back to equation 4 for our bandwidth and some of our other forms for equations for Q factor, for our quality factor Q, as well as our resonant frequency, in order to find these equations, or rather these values, in a slightly different way. So that can be a good way to double check if you have time or if something doesn't quite seem right.